On here. So what we covered before the break, that was known as the central limit theorem. Okay. So that was what we covered before the break. This is the notion that sampling distributions will end up following the normal distribution, okay? Central limit theorem, we might also call it CLT. Yes, question? Theorem. That's like theory. This is an M. Theorem. Yeah. Theorem. It's a central limit theorem. And yeah, it's the idea that our sampling distributions will follow the normal distribution. This is actually a remarkable finding. But there are a few conditions, okay? A few conditions must be met for the central limit theorem to be applicable. Okay, and so these three are the random / independent condition, and that means our sample must be selected randomly and the individuals are selected independently of each other. Okay, and that's, but if it says that the sample is selected randomly, that generally means the second part, that they're selected independently of each other, is also true. Okay, so when you check to see if you can apply the central limit theorem, look for the phrase, look for an indication that the sample was selected randomly. Okay. And in the next condition, we want to make sure that the sample is not too big and not too small. So these are actually two conditions, and so here we call this the large sample condition. Okay, so our sample cannot be too small. We want to make sure our sample is large enough. Okay, and so for this to be the case, there's two math things that you need to do. Okay, so n times p must be bigger than 10, and n times 1 minus p must also be bigger than 10. Okay, so both n times p and n times 1 minus p must be larger, must be 10 or more, must be at least 10. Okay, so both of those numbers, whatever they are, have to be at least 10. If not, the large sample condition is not met. Okay, and the last one is the big population condition. Okay. Basically, your sample cannot be more than 10% of the population. Sample cannot be too big. Sample must not be over 10% of the population. So all of our rules kind of follow this rule of 10 thing. So basically, the population, you just have to make sure that the population is at least n times 10. Okay. And if that's not met, then your population, big population condition is not met. Can you guys all see this? All right, so let's try a couple examples. I will write out a scenario, and you don't have to copy down the entire scenario. Well, I mean, you can. It'll be in your notes, but I feel like your time is better spent thinking about the scenario. And then there's going to be questions in your practice quiz that are also similar to give you some practice as well. Okay, so you have these three conditions: random independent condition, large sample condition, and big population condition. Okay, so let me start up Word here. We're going to do a blank document. Okay, so you don't have to write this out, but I'm going to just write out a scenario. So we will see a researcher decides to perform a study. Oh, shoot. Where's my view? Print layout, page width. No, it's too small. Okay. So let me just blow this up. Okay, a researcher decides to perform a study. He randomly selects 85 people, and 85 people. He asks if they drive an SUV. Okay. 20% say yes. Okay. All right. Are any conditions violated? Okay. So a researcher decides to perform a study, I guess, to see what proportion of drivers drive an SUV. Okay. So let's see. Let's see. So what are the conditions? The conditions are random independent, large sample, big population. So let's try this out. So I'll list these off again. Independent / random. 2 is large sample. And 3, big population. Oops. Okay, so we want to know, is anything violated here? So in this problem, a researcher decides to perform a study. Okay. Is the sample selected randomly? Yes. Okay, so condition 1 is met because it says he randomly selects people. Okay. Is the large sample condition met?
No.
Okay, so what is n? 85, and what's p? So we only have p hat, but that's okay. P hat is 20%, so we're going to use this, okay? So we want to just make sure n times p is greater than or equal to 10, and n times 1 minus p. So what is n times p? 85 times 0.2, that gives me 17. And 85 times 1 minus 0.2 is 0.8. What does that give me? That gives me 68. Okay. These are both bigger than 10. So number 2 is met. Okay, what's the third condition? The big population condition. Okay, what is my population in this problem? Huh?
85.
No, my sample is 85. What's my population? The population is everyone relevant to my research question, right? So who would the population be? Yeah. It's not the number of drivers who drive the SUV. We want to know the proportion of drivers who drive an SUV. That's the quantity of interest, is the proportion of drivers who drive an SUV. But everybody relevant to this would be all drivers, right? The population is all drivers. Okay, and my quantity of interest is the proportion that drive SUVs. Okay. So my population is all drivers. To check if this condition is met, I said my population needs to be at least 10 times my sample, right? So my sample is 85, so 10 times my sample is 850. Do we have more than 850 drivers total if we look at all drivers? Yes, okay. Very clearly we have millions of drivers. Even let's say we're just looking in the United States or whatever. We have millions of drivers. So I don't have to worry about the population not being big enough. So the population is big enough. So this is met, number 2 is met, and number 1 met. Okay, so all 3 conditions are met. Okay, so sometimes the problem does not explicitly state what the population is, and you just have to do a little thinking there. Okay, the population, you always know, is everyone relevant to the question. So this would be all drivers. Are there any questions here? Okay, let's try another one of these. Oops. Okay. A student decides to go to the subway station and ask strangers he meets if they enjoy eating at McDonald's. Okay. He wants to know the proportion of all Americans who like McDonald's. He surveys 150 people. 30% say they like McDonald's. Everybody likes McDonald's. Maybe this is like 90%. I don't know. Okay. All right. So in this scenario, don't shout out your answer. Just think about it, okay? And you tell me if any conditions here are violated. Okay, so again, don't shout out your answer. Okay, so go ahead and tell me, are any conditions here violated?
One.
Yeah, the random and independent condition, right? So what is the population he wants? All Americans. This is the population, okay? So number one, the population is all Americans, but is he getting a random sample of all Americans? Okay. Even if he selected people randomly at the subway station, okay? So we could say he asks random strangers at the subway station, is he still going to get a random sample? No, okay? So this is not a random sample of the population. Okay, so he may even be able to manage a random sample from the subway. But that's not a random sample of all Americans, right? Because that's just going to be people in that city at best and people who ride the subway. Okay, so we're not going to get anybody who doesn't ride the subway. Okay, large sample, is that met?
Yes.
Yeah, that's met. Okay, n is 150, p is 0.3. Okay, so n times p is going to be 45. N times 1 minus p is going to be 105. Okay, you can check the calculator. And then lastly, big population. Again, my population is all Americans. So n times 10 is 150 times 10, or 1,500. The population is bigger than 1,500. Is that okay? All right, let's try another one. Okay. So a school, I will say a local elementary school, decides to take a survey of its students to see if they like the PE program. Okay. There are 672 students at the school. The administration randomly selects 120 students to be surveyed. Of the surveyed students, 80 of them like PE. Okay, so again, think about the your answer here. Don't shout it out. We want to know, are any conditions violated here to use the central limit theorem? Okay, right? So to use central limit theorem, must be random and independent. You must have a large sample. And you must have a big population. Okay, is anything violated here? All right, let's go through them one by one. Are my students selected randomly?
Yes.
Yes, it says randomly selected. Okay, so this is met. Is the sample large enough? Okay, so here we don't have P. P is not given. Okay, but we have a count. Okay, and so another way is that you just need at least 10 yes and 10 no. So this is, so if P is not given, you can just check for 10 yes and 10 no. Okay, so how many yeses do we have? We have 80 yeses, 80 people who like PE, and how many no's? 40 no's. Okay, right? If we have a total of 120 in our survey. So both are bigger than 10. So our large sample condition is met. Okay, so even if P is not given, you have at least 10 yeses and 10 no's. Okay, sometimes the book calls this successes and failures. Whatever we want to call it, okay? These are arbitrary labels. Yes and no, successes, failures. You need at least 10 in one category and 10 in the other. Okay, so that's met. What about the big population condition? Okay, what's my population? I have 672 students, right? So the population is all the students at the school. 672 students. And how many are in my sample? My sample is 120. So my population needs to be at least n times 10. I should, for a sample of size of 120, I need at least 1,200 students. And I don't have 1,200 students in my population. Okay, so population is not big enough. Okay. You know, if I shrunk down my sample to, let's say, 20 students in this case. Okay, so maybe I could shrink this down to 20, and then maybe I will have 15. Okay, so if this were the case, so if I have 20 students and 15 of them like PE, here are any conditions violated here. Yeah.
Well, there's not at least 10 yes and 10 no.
Yeah, we no longer have 10 yeses and 10 no's. I have 15 yeses, but I only have 5 no's. So in this case, so now if I shrink my sample size to size 20, my population is big enough, but now my sample is too small. Okay? So now condition 2 is violated. Sample is not large enough. Is the distinction here clear? Is that okay? Okay. So you have a few questions like this in your practice quiz. I think that's good. And
is there any in the homework like this that touches on the homework?
That touches on the homework. Now let me see. I think there might be, but it's not. It might be worded a little differently. Okay, it'll say things like check the conditions to determine whether you can apply the central limit theorem. Okay, and it's usually as part of a larger problem. Okay, but on the quiz I'm going to separate it out. I'm going to do checking the conditions as problems in of themselves, and then for the other problems I'll say the conditions are met, do the problem. Like if 30% of the candies in the tub are orange, and you take a sample of this, what's the probability you get 40% orange or something like that? Okay. All right, so we got one more thing to do, and that is doing our inference. Okay, and so this is called confidence intervals. Okay, do you guys have your reference tables? I just want to make sure as part of your reference tables you have the oh, you know what? You don't need the t-table. Not for today. Okay, I apologize. But you guys have the t-table as part of your reference tables? It's the should be the 3rd page. Yeah. I'm sorry, I forgot. We don't need that today. You'll need that in a couple weeks. Okay. So here we've got confidence intervals. All right? And so the idea behind the confidence interval is kind of that question I asked much earlier on. I said, if your sample has this proportion, what does that tell us about the population? I said, if my sample ends up being 36% orange candies, what does that tell me about the bathtub? Okay? So, and we came just to this vague conclusion that the population proportion P should be in the vicinity of my sample proportion P hat. Okay, and the confidence interval, we just kind of make this a little bit more precise. So here's the big picture. Okay. We do not know the population proportion P. Okay, we take a random sample of size n. We observe a sample proportion of P hat. P hat, okay. We will make a range or an interval of plausible values of P P based on what we see in the sample. Okay, so for example, okay, I take a random sample of candies from the bathtub. Okay. My sample is 36% orange. I do not know the actual proportion orange in the bathtub. Okay. But because my sample is 36% orange, I will make an interval. Okay, so I might say my interval is 36% with a margin of error of, let's say, 5%. Okay? Or this can also be rewritten as 0.36 plus or minus 0.05. Okay? And so now, essentially, I'm saying I am reasonably certain, or I am reasonably confident that the proportion, the actual proportion that's orange in the entire bathtub, actual proportion P, proportion of orange candies, is between, so what's 36% minus 5%? Percentage points being? Is between, so I would do 36 minus 0.05, I would say between 0.31 and on the upper end, what would I have? It would be 0.36 plus 0.05, so what would that give me? And 0.41 orange. Okay, so this is where we're headed. So I don't know how much in the bathtub is orange, but I took a random sample, and my random sample gave me 36% orange. Okay, and so because of that, I can say something like, well, my random sample should be somewhat close to the actual proportion, but I don't know if the actual proportion is higher or lower than my random sample. So I created a range. We calculate the margin of error, and I'm going to show you how to do that in a moment. But in our case, we got 5%. So we're going to say 36 plus or minus 5%. So 36 plus 5 percentage points takes me to 41%. 36 minus 5% takes me to 31%. Okay? So I'd say, I'm reasonably confident that the actual proportion of orange candies is between 31 and 41% orange. Does that concept make sense, what we're doing? Okay, so now we just have to get into the math of getting this margin of error. Okay? Okay, so there are 4 numbers that you either need to memorize or make sure you have written on your note card, okay? 4 numbers to memorize or write on your note card. Okay. Do not come crying to me next week saying you forgot to write these on your note card, okay? Because I'm telling you right now, you either need to memorize them or write them on your note card. Okay? And this is, and it talks about, it relates how confident you want to be. Okay? So the confidence level, and this matches to what we call a critical value. Okay? And so we're going to say if you want to be 80% confident, 90% confident, 95% confident, or 99% confident. Okay, your critical value is 1.28, 1.645, 1.96, or 2.58. Okay, so either, again, either memorize these or just make sure you have them written on your note card. I'm going to put stars all around these. Yes.
So the 80% is that correlated to?
Yeah. So okay. So yeah, these go with each other, right? In case it wasn't clear. Okay. So the 99% matches to the 2.58. 95% matches to 1.96. 90% goes with 1.645, and 80% goes to 1.28. Okay. So you need these pairs. Memorize your one. Okay. All right. So the confidence interval. For P, the population proportion P, based on P hat. Okay. So P hat is the proportion we get in the sample, and based on that, we create the confidence interval for P, the proportion in our population. And that is P hat plus or minus our critical value. Critical values also called, in our case, these are Z stars times the standard error P hat times 1 minus P hat over N. Okay. Notice we use the hats here versus when we did the central limit theorem problems earlier, there were no hats. We have a question.
What's that on the corner?
It's a star. Okay, to indicate it's coming from my table of stars here, okay? This is known as the critical value, okay? So and this thing is called our standard error. And then Z star, these two combined create our margin of error. Okay, so when news organizations, they report the results of, political polls and stuff like that, they'll say candidate XYZ, Donald Trump is has this percentage popularity with a margin of error of this, right? 3% or something like that, okay? When they're talking, you know, if you were to ask about the math, it's a combination of a critical value and a standard error. And usually they pick something, probably 95% is their go-to value, but they might choose lower or higher confidence depending on what they want. Okay, so let's try an example here. Let's try a problem out. So, okay, so let's say we want to know the percentage of students who liked PE. Okay. Will you guys hate me if I do a survey here and you can just raise your hand if you enjoyed PE in class, in school, in your time in school, or are we not doing this? Okay, go ahead, right? Go ahead and raise your hands if you like PE. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so this is not a random sample, okay? But, okay, so we surveyed, how many people I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5. Okay, so we surveyed 25 people, and 13 said they like PE, or liked PE. Okay, all right, and so let's make a confidence interval. Let's make a 95% confidence interval for the proportion who like PE. Okay, so again, technically we can't do this because this is not a random sample. But let's pretend that you guys were a random sample. Then we can use this to make inferences about the population. But you guys are not a random sample, right? And somehow, you know, whatever it is. Okay. So what is p hat? P hat is the proportion in our sample, right? So what is that? It's going to be 13 divided by 25, right? This is the proportion that likes PE in our sample. So what is 13 divided by 25? 52%, right? Okay, so this is the proportion that likes PE in our sample. 52% of students in our sample like PE, okay? How big is my sample? Sample size is 25, okay? So technically we should be checking conditions, and I'll just tell you that the conditions are met. But is our large sample condition met? How many yeses and how many nos do we have? We have 13 yeses and 12 nos, right? So both of those numbers are bigger than 10, so we can still go on. Okay, so the formula for the confidence interval is p hat plus or minus z star times the square root of p hat times 1 minus p hat over n, okay? So I have p hat, so I'm going to just plug in the numbers I have here, okay? So p hat is 0.52 plus or minus, okay? We'll go to our z star later. I'm going to just square root, and I'm going to do, every time I see p hat, I'm going to plug in 0.52. times 1 minus 0.52 divided by what's n? 25. Good. Okay. And z star depends on what level confidence. Okay, so when we read the problem, it says a 95% confidence interval. Okay, I have abbreviated confidence interval as CI. So look at your little table of 4 numbers. What is the number that corresponds to 95%? 1.96. So our z star is 1.96. Is that okay with everybody?
I'm sorry, would you 196?
So z star is 1.96. This comes from my table of 4 numbers. Remember I said there's 4 numbers you need to learn. For 95% confidence, we're using 1.96. Okay, and so at this point, now we just solve all of this. All right, so we do 0.52 times 1 minus 0.52 divided by 25. And I take the square root of that. And then I multiply this by 1.96. So I get this slightly atrocious 0.1958. Okay, so I'm going to have 0.52 plus or minus 0.1958. Okay, so I will do 0.52 plus that and 0.52 minus that. So 0.52 minus 0.1958 is 0.3242. That's on my low end, right? And on my high end, I do 0.52 plus 0.1958, and that takes me to 0.7158. And this is on my high end. And then I'm going to say some statement about this, and I'm going to say I am 95% confident that the proportion of students who like PE is between 0.3242 and 0.7158. This might come as a surprise to you. PE was not my favorite class. Okay. So anyway, here we go. So 95% confident that the proportion of students who like PE is somewhere between basically 32% and 72%. Okay, I know that's a huge spread, right? If you want to be 95% confident about what proportion of students like PE, we're saying something like it's between 32% and 72%. That's a pretty wide range, right? It's like, what percentage of people are going to vote for, the Republican candidate? Between 32% and 72%. That's kind of, it's like, oh, that's really helpful. But that's because we surveyed 25 people, right? We've surveyed 25 people. You're not going to have a whole lot of information about the population just because even you guys aren't a random sample and not representative of the population either, certainly not, because you're all from Los Angeles County, Southern California, and you're in this highly educated thing. At least going to college makes you automatically more educated than a great percentage of the population. So we're not representative. But if this were a representative population, it's still, only 25 of you, and so the conclusions we get are not quite useful, okay? But is this okay? We're making a statement. And notice I have to say I'm 95% confident that the proportion of students, this is proportion of students in the population, right? Proportion of all students in the population who like PE is between this and this, okay? So let me try another example for you guys to try out. And we'll just make sure we're all understanding this. Okay, so we're going to take another survey. We have another study, and we want to know, you know, the percentage of American voters who will vote for candidate ABC. Okay, so let's say, you know, Mr. ABC is running, or Mrs. ABC. Whoever candidate ABC is, we want to know who's going to vote for this person. All right, so an organization surveys, we'll say 540 random voters. Okay, and we will say 295 say they will vote for ABC. Okay, make a 90% confidence interval for the proportion of all voters, of all American voters, who will vote for ABC. Okay, so go ahead and try that out. I'm going to pause the video while you guys work on this. Okay, let's take a look. All right, so I'm going to just go ahead and write the equation for a confidence interval. All right, so let's go through a problem and figure out these things. Okay, so P hat is the proportion that's going to vote for ABC in our sample, right? We want to know is the proportion of all voters who will vote for ABC. That's P, but in our sample, how many said they're going to vote for ABC? 295 out of 540. Okay, and so I do that too. Here, I'll use my actual calculator here. 295 divided by 540, and I get 0.5463, right? Okay. All right, so I'm going to just plug all of these things in here. For a 90% confidence interval, what's the Z star I use? 1.645, right? Okay. And I'm going to plug in P 0.5463 every time I see P hat. And what is my N? My N is 540. Okay, so when I do my calculations, I like to figure out the standard error first, and then I multiply it by 1.645. You can do it however you want. But notice that I'm going to punch it in maybe a little bit differently. I already have kind of this 0.5463 already in my calculator. So to get this part, I'm going to just do answer. because that's essentially 0.5463 times, parentheses 1 minus the answer, divided by 540, okay? So that gives me the part inside the square root. I'm going to take the square root of that, and I get 0.0214, okay? So I'll have plus or minus 1.645 times 0.0214, and I have 0.5463 plus or minus that, okay? So now I'm going to multiply this by 1.645, right? 1.645 times 0.0214, and I get 0.0352, okay? And so if you did a little bit of rounding off, your answer might be just ever so slightly different from mine, but don't sweat it, okay? So I have 0.0352. All right, so maybe just quick questions, okay? What is my standard error? What is the value of the standard error? Which, you guys, 0.0214. This is the standard error. Okay? And what is 0.0352? What is this thing called? This is called the margin of error. Okay? So, you do want to learn the difference between the standard error, which maybe I'll write it completely out here rather than abbreviate, but it's, or SE, the standard error. The standard error is this part. When you multiply the standard error with this thing, what is this thing called? The Z, or the critical value. So yeah, when you multiply the standard error times the Z star, or the critical value, then you get the margin of error, okay? So I have 0.5463 plus or minus 0.0352, and so now we can get our final answer. 0.5463 minus 0.0352, and I get 0.51111. So on 5111, this is on my low end. And let's go back and change that minus to a plus, and I have 0.5814. Okay, so now I can say something like I am 95% or not 95, 90% confident, I apologize, 90% confident that the proportion of voters in the entire population, right? Proportion of all voters in the population who will support ABC is between 0.5111 and 0.5814. Okay? So here's a question. Can we be confident, are we confident that candidate ABC will win?
90% confident that he will?
Yeah, we're over 90% confident, because to win you just need at least 50%, right? And what do we see? We see 50% is not in the interval, okay? So 50% is outside of the interval, right? Okay, so we are confident that ABC will have at least half the vote, which means in a regular election, that means a win, okay? But let's say there was some crazy rule, right? You needed at least 55% to win. Let's say if it's less than 55%, there's a runoff or something, I don't know, something stupid, okay. So let's say you need at least 55%. Are we confident that candidate ABC will get at least 55%? And the answer to that is no, because it goes from 51 to 58%, and 55% is kind of in between there. So any value between 51 and 58 is technically plausible. So it could very well be 52% or even 51%, you know? So anything in between the things are plausible values. So we would say we don't have evidence that it's not 55%, okay? But we do have evidence that it's not 50%, and we actually have evidence that it's going to be more than 50%. Is that okay? All right, so you've got some homework going over this, and a practice quiz. Okay, so practice, and we'll see you guys next week for the quiz.
Attendance?
Yeah,